of the world as we know it. I feel fine.
Hey guys, how's it going? Welcome back to our second part of acid-base chemistry. Today we're going to be starting a discussion of the different definitions of an acid and a base. There's technically three different ways we can define an acid and a base according to three different theories proposed by three different scientists. We're going to focus on one of them in this video today. There is another short video that correlates to this one that's going to cover the second way we can define an acid and a base. And then the third definition of an acid and a base is very broad, rarely used until you get into higher levels of chemistry. In fact, it used to be part of the AP curriculum, but they took it out of the AP curriculum as well. All right, so the first theory of an acid and a base was proposed by a Swedish scientist by the name of Svante Arrhenius. We're going to focus on him today. So for our notes and where this is covered, if you're in honors chemistry, we're going to be looking at Learning Guide 11.2, and we're going to be studying pages 4 through 6, number 11. That's where we're going to stop. The second definition of an acid and a base will be covered starting with objective 12. In college prep chemistry, if you're following along, this begins on page 5, Roman numeral number 4, the Arrhenius theory of acids and bases, and this will cover the material up through page 7, right before Roman numeral number 6, the Broadstedt theory, which again will be discussed in the next video. So Svante Arrhenius was a child prodigy, extremely gifted, intelligent young man. He was studying to get his PhD and doing research for his PhD in Sweden when he came up with this theory. And he was actually the age of a high school student. So he was way advanced. He was studying the conductivity of certain solutions and then trying to differentiate them into three categories, which you remember from the previous video. We talked about the fact that acids, bases, and salts can all conduct electricity because they possess those free-moving ions. This part of the unit is going to deal with the same material. Svante Arrhenius tried to break those three groups of electrolytes into acids, bases, and salts. And in all honesty, his theory was not well received by the people that he was working under at university when he was trying to get his PhD, to the point where they actually gave him the lowest grade possible to receive his PhD. But then years later, it was discovered that his theories were correct. So here's the Svante Arrhenius definition of an acid and a base.
In 1884, a Swedish scientist by the name of Svante Arrhenius pioneered the study of acids and bases on the molecular level. While working towards his PhD degree, Arrhenius studied electrical conduction through solutions. Arrhenius was puzzled as to why some solutions conducted electricity and others did not. He believed that some compounds, such as sodium chloride, split into ions when dissolved in water, while others, like sugar, did not. Arrhenius devised a theory stating these free ions were responsible for conducting the current. After concluding his work on electrical conduction, Arrhenius went on to apply his knowledge of ions and their properties to define and explain acid-base chemistry.
One more.
When acids, bases, and salts ionize, they form ions in solution. Arrhenius could not see compounds ionize, but he could infer the ionization by measuring the resulting increase in electrical conductivity. These and other experiments led Arrhenius to propose the first accepted definition of acids and bases. Arrhenius defined an acid as a substance that ionizes in water to release positively charged hydrogen ions into solution. He defined a base as a substance that ionizes in water to release negatively charged hydroxide ions in solution.
So this was the first accepted theory of an acid and a base. Acids dissolve in water, and when they do, they make H plus as the only positive ion in solution. And when bases dissolve in water, they break apart, and the only negative ion they make in water is OH minus. So this was the first accepted definition of an acid and a base. So then as he continued his study of acids and bases, he then looked at what differentiate a strong acid from a weak acid and a strong base from a weak base. So to illustrate that, take a look at this model that we have coming up on the screen. Okay. So here is a beaker full of what is currently water. You can see that there's different choices over here on the right. So we're starting with water. Now you would think that when you look at water, if you could look at water under a microscope or through a magnifying lens, you think all you would see are water molecules, but you actually don't. We're going to get to that a little bit later in the unit. We're going to get to the concept of pH again later in the unit. But if you were to take this pH meter and put it into the water, you would see that the pH of water is 7. That's the pH of a neutral solution. Now, take a look at the difference between a strong acid and a weak acid here. If you were to be able to look at these solutions under a microscope or with a magnifying lens, if you take a look at the strong acid, you would see an abundance of free-moving ions. And if you look at the reaction down here at the bottom of the screen, when a strong acid reacts with water, you get free-moving ions. You get this hydronium ion, which is a positive polyatomic ion, which we're going to get to in a minute, and this negatively charged cation, A minus. And in a strong acid, you have an abundance of positive and negative ions. Now, a lot of students have a tendency to have a preconception that a strong acid and a weak acid is based on pH. The lower the pH, the stronger the acid, and the closer it is to 7, the weaker the acid. Some students have a tendency to think that the molarity is what determines a weak acid from a strong acid. So a strong acid that's 12 molar is stronger than one that's 6 molar, which is stronger than one that's 3 molar, and so on and so forth. It's not molarity and it's not pH. Acids are determined in terms of their strength by how much they break apart into free-moving ions. So a strong acid like this, if you could look at it under a microscope, would yield nothing but free-moving ions. A weak acid, you'd have very few free-moving ions, and most of the acid molecules would stay together because if you look at the double arrow and what we studied in the last unit, weak acids reach equilibrium and they don't completely break apart. So the less free-moving ions you get, the weaker the acid is. And the less it breaks apart, the weaker it is. Strong acids, they don't have that double arrow. They just have one arrow because it completely breaks apart into free-moving ions. That's the difference between a strong acid and a weak acid. Strong acids completely break apart. Weak acids only partially break apart. Less free-moving ions, and they reach equilibrium. Now, what about bases? Bases are the same thing. If you take a look at the bases in this presentation as well, you'll see that a strong base, when you put it in water, it completely breaks apart into these free-moving ions, and you get a lot of these hydroxide ions, which are noted in blue here. And notice that there's an arrow only going in one direction. A weak base, on the other hand, reaches equilibrium, and you only get a few free-moving ions for every one of the base molecules that you put into water. So strong acids completely break apart. Strong bases completely break apart. Weak acids only partially break apart and they reach equilibrium. Weak bases only partially break apart and you get less free moving ions. That's the big difference. Now, what happens when an acid dissolves in water? If you saw in that presentation, you might have noticed that there weren't any H plus ions in the solution, and instead they were replaced by a polyatomic ion with the formula H3O plus. Well, here's the reason for it. So if I were to draw a beaker, here we go. So if I were to draw a beaker, I don't know why that's straightening out like that. Oops. There we go. All right, so I got a beaker, and in that beaker, let's say that I've got water. So remember, water has the formula H2O. It's got an asymmetric shape that looks something like this. If you take an acid and you put it into water, so let's say that my acid has a general formula HA. If I take this acid and I put it into water, it's going to break apart into H plus ions, and you're going to get the A minus ions from the negatively charged nonmetal that is found in the acid as well. This positively charged hydrogen ion is going to attach itself to those unshared electrons on the water molecule. When it attaches itself to that negatively charged electrons on the water molecule, you end up with a polyatomic ion, that's why we put the brackets around it, with an overall charge of +1, which is found on our reference tables in table E. So if I take water, H2O, and to it I add an acid, which contains H+, together they'll form a polyatomic ion with the formula H3O+, and this is called hydronium. So all acids contain this hydronium ion because every one of the H plus ions that are in water, they're going to be so strongly attracted to the unshared electrons on the water molecule, and it's going to form a bond that as a result leads to this reaction over here, the production of the hydronium ion. So these acids do break apart and they do make those H plus ions, but every one of those H plus ions end up combining with water molecules in the water, producing the hydronium ion. All right, the last little part of this is the different types of acids that exist. At the end of this, so at the top of page 6, in our honors notes and in the definitions at the beginning of the unit for college prep and at the top of page 7, we have one last thing that I want to talk about, and that is the classification of an acid based on how many hydrogen it has. Do a little jumping around here, make it easier.
Acids may be classified by the number of ionizable hydrogen ions the compound contains. You can think of an ionizable hydrogen as one that is capable of being donated to solution. A compound such as hydrochloric acid, HCl, is called a monoprotic acid because upon dissociation, the compound donates one proton to solution. Likewise, sulfuric acid, H2SO4, or any acid that contains two ionizable protons, is known as a diprotic acid. Phosphoric acid, H3PO4, contains three ionizable protons, and therefore is known as a triprotic acid.
So they gave a couple good examples here. They gave an example of sulfuric acid, which contains two hydrogens, di, phosphoric, which contains three hydrogens, tri, and hydrochloric acid, which contains one hydrogen. We use the prefix mono. This becomes extremely important in two presentations when we talk about titrations. So remember this when we get to titrations. All right, guys, that's all for this video. We got another short one related to this and the second definition of acids and bases. Take care.